let me explain one by one. So first of all, so we take the normalization from the a plus I input. So it is to consider neighboring nodes in the normalized weight. So when you compare before and after, sometimes, so before the normalization, it is difficult to evaluate. So it is to give the maximum and the minimum weight to the node, to the node. So it is the purpose of the normalization, right? Otherwise, some node has 10 degree and some node has 1 degree, and some very popular node is getting so many scores from the original degree, right? So to give the minimum maximum, and we normalize the score, and we are able to prevent the numerical instabilities and try to prevent the vanishing exploding gradients in order to the model to converge. So I will give you more examples for that. Now we consider a feature matrix. So now we have the normalized adjacency, which includes the neighboring information, and we try to consider the weighted sum of the neighboring features. So how would you possible to compute the weighted sum? So forget about the normalization. So now we have the adjacency. So the dimensionality, something like this, right? And the feature matrix is the V and F, right? And assume that we are interested in the first node, and their adjacency is something like this. And we multiply, so we first consider the first feature. So we multiply something, is like this, right? It is this V, right? So it's same as the length is the same as the number of vertices. And when we multiply this, if the neighboring node has non-zero values, we consider their feature, right? And in this case, we have this, the neighbors to the second and the fourth the node, right? How about drawing this? And 1, 2, 3. This is connected here and here, right? And all others are 0. So when we multiply this, for example, the value 1 features for all the vertices in the first feature. So we multiply this, we ignore this, right? We ignore this. We're considering this and this. And the final value for the, let's say this is the H, for this H matrix, the final dimensionality will be V by F, right? But in this case, first value is 2, because the 2 is from the 1 plus 1, right? So it is called the sum of the neighboring features. So it considers connected neighbor and sums based on the adjacency at the corresponding position. Now we see this is normalized. And then assume that this has some value. So for example, this is 0.5 and 0.5. This is example. And then this is normalized between 0 to 1, and we consider this and this, and it's gonna be 1. So that's how we call this multiplication as weighted sum. So let me give you the actual example. This is the very simple input graph data. We define the graph. I define the graph using the popular Python graph network library, which is called network X. So we imported the network X library and we put the name G, and now we have the variable G, and we add nodes. We have 6 nodes and define the edges between the 6 nodes, and like this, and we add edges between the given edges. So their visualization is like this. And we can print out the adjacency from G. It is a NumPy matrix. The shape is 6 by 6, and we give just one feature. This is a feature matrix. So adjacency is like this. This is from the input edge information, and I gave the artificial feature for the first and fourth node, because this one and this one, so it is connecting 2 triangles, so I give them 1, otherwise I put the 0. So for just convenience, so it is some connecting properties, so that's why I give the features for them. And we can print out this, and the shape is 6, 1. And when we multiply this, AX, so this is the sum of the neighboring nodes. So this is before the normalization. Before normalization. So we get the dot product, and then we are able to get this. So all are getting the same value. It's because it is aggregated. 4 is the 1 is from here, 1 is from here. I'm sorry. This one, the feature is from this one. For this, the feature is from here. For this, features 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 from here, and so on. They all having same value. This makes not possible to disambiguate between the nodes, particularly between the connecting nodes and the others, right? So now we consider the self loop. How would you add a self loop in the graph? We just make a for loop, and this is the edge, and we give the edge between the I and I, so it gives edge something like this. And now the network has the self-connecting node, right, and so on. So this is the new graph, and this is the new adjacency, and when we multiply the x, now we having different values, right? finally we are getting different value because it is considering the node itself, right? The nodes themselves, and that node has different value. So to disambiguate the connecting node and the other, it was important to consider themselves, right? It is important to all the network data, right? To decide their own representation, it is important to consider themselves as well, right? It is to decide your gender. Your friends are important, but we should consider our information as well, right? It is to decide your department using network data, student network data. To decide your department name, we should consider our own information as well. What kind of courses we are taking, right? So that's why the setup loop is important in this multiplication. This is also called propagation. So we propagate the neighboring features using the edge, right? By considering the self edge, we are able to consider their own information. That is the key idea of the propagation. So when you see this, the same slide, we notice that the scores are not normalized, right? Even though we're able to disambiguate between the connecting node and the others, but the values are not normalized. You may have exploded the values or a very small value in your actual learning when you train the very complex graph network data. You may fail the learning. So in this case, for the GCN, so we are able to imagine many different normalization, right? You just use directly multiply by the inverse. It makes you the sum of the row-wise information to exactly 1. In this paper, slightly different normalization, and they were able to find in practice the experiment returned better result, but it doesn't have to be this normalization. It depends your data set. So we just stick with the original normalization. By multiplying d to the minus 0.5, so d is here, but we multiply this to the both side of the a hat. A hat was a plus I, right? So we compute this, we compute d to the minus 0.5, and then when we compute this, you are finally getting this. This is between 0 to 1. Right? It looks better. So now we're able to consider nonlinear projection. So now we are able to propagate the neighboring features, right? Before we consider nonlinear projection, we're still able to propagate neighboring features. But when you have simple graph data, you're still able to identify the connecting node and the others. What about you have the very complex data? Then you need some power of the neural networks. You give the nonlinear projection, we are able to find more complex the latent representation. So for that, we just multiply the trainable matrix W. So by multiplying W, so which is the same as the adding the neural network layer, right? Fully connected neural network layer. And then we use Lambda function to add nonlinearity. And then finally we get the node embedding of the V. So from the H, the dimensionality was the V by F, right? Depending on the shape of the W, the final dimensionality could be different. Assume that the W corresponds to F by some what could be the dimensionality? So let's say T, and then the H, the dimensionality of H could be the V by T, right? Now we have the T dimensional representation for the all node. That is the embedding. So currently we're considering the just one layer of the graph convolution neural network. So we haven't considered multiple layers. This is the first layer, the just one layered representation. We're still able to use this for node classification or link prediction. So we can generalize the GCN layer using the notation L. So we can generalize the representation. So we stack over from the input. So this is the first GCN, so another GCN. Let's say this is Lth layer. We have the Lth layer, and the GCN, we represent their embedding as a function f. It takes the previous layer embedding and consider the adjacency once again. So we had this output from the first layer, so T dimension. So these should be something like T by TL, for example. So this is for the first layer representation. This is from the L layer. And we aggregate the embedding, the neighboring embedding. So similarly, we propagate the embedding information using the adjacency. And then we get the weighted sum and adding nonlinearity and project into another space. Project to another space and add nonlinearity, we get another embedding, the Lth layers embedding. That's all. So we keep stacking the GCN layer deeper and deeper. We are able to get to another representation. Choosing the size of the layers, the number of layers is the hyperparameter. So using the validation data set, we choose the proper number of the GCN layers. So overall, here we use the representation, the H. The H is a node representation. I'm keep using different notations, sorry about that. So now we have V by D representation. Assume that we have the input And to decide representation of the D, we considered first, at the first layer, we first consider first hop neighbor at the first layer, first addition layer. So connected to E and E, F, C, and D, because we consider the self-connecting node. D, C, the E, D, E, F, C. E, F, C. We also consider the self node, so I didn't visualize from the D. So it was used for something like this. So that's all. So let me clarify my explanation here. So to decide the representation of D, at the first layer we got the all nodes, the representations of the all nodes, right? D and C, D and A, B, D, F. And they have their own representation in the latent space, right? And then we propagate once again to decide the final representation of D. We consider E, F, G, and D. So if you understand the previous propagation step, so it's not a big deal, I believe. So any questions, and let me know.